How it's made, capping and sealing, raw materials and pre-form production.
Under carefully controlled temperature and pressure, the individual molecules link together to form long chains known as polymers. These chains are the foundation of modern plastic manufacturing. Depending on the type of monomer used, manufacturers can create different kinds of plastics: PET for water bottles, PE for packaging, or PP for bottle caps. After the reaction, the polymer takes on a thick liquid or soft solid form and must be cooled to stabilize its structure. This step marks the transformation from a chemical substance into an industrial material, ready for pelletizing and shaping into finished products. When the polymerization process is complete, most of the polymer is cooled until it solidifies, creating a standardized form that is easier to store and transport. The solid material then moves into a cutting or extrusion system, where it is shaped into small plastic pellets known as nurdles. These raw plastic beads are usually round or slightly rice-shaped, with a milky white or transparent appearance. Thanks to their compact size and uniformity, nurdles can be stored, packaged, and shipped over long distances without losing their shape. What many people don't realize is that every year, the industry produces millions of tons of nurdles, and even a small amount leaking into the environment can cause serious pollution, as they are almost non-biodegradable. During pelletizing, manufacturers can add various additives such as heat stabilizers, UV blockers, colorants, or strength enhancers, depending on the needs of the final product. Once finished, the pellets are packed into large sacks or containers, ready to leave the plant and head to manufacturing facilities. From there, they will be melted, molded, or blow-formed into countless familiar items like food wrap, bottle caps, or rigid plastic bottles. From these uniform plastic pellets, manufacturers move on to the shaping stage, turning raw material into preforms, the starting point for a bottle's final form. In PET bottle plants, the pellets first go through quality checks before being fed into a heating and extrusion system. Heated to around 500 degrees Fahrenheit, the molten plastic is pushed through a mold that shapes it into short, test tube-like pieces called preforms. These have thick walls, a threaded neck for the cap, and are engineered to handle heat and pressure without deforming during transport or further processing. Preforms serve as a precise way to control the amount of plastic used for each bottle, ensuring consistent volume, weight, and durability in the final product.
Next comes blow molding, the heart of bottle manufacturing. The preforms are heated until they reach a flexible, rubbery state. They are then placed into precision molds with high-pressure air rapidly inflates them into the exact shape of the bottle. In just seconds, the plastic expands, cools, and locks into its final forms. Quality checks ensure every bottle meets strict standards for thickness, clarity, and durability. From concept to finished product, modern blow molding technology delivers millions of lightweight, recyclable bottles with consistent precision, ready for filling, packaging, and shipping. Filling systems. Take it away, Sullivan.
Once the bottles are fully processed, they move on over to the filling station. We'll take a look at different filling styles and key operations for different types of liquids. Here the bottles are flipped over, they're rinsed first with water, then a combination of food-grade detergent, hydrogen peroxide, and then rinse again with sterile water and blow-dried with air or nitrogen. Here we'll take a look at the different types of nozzles. On the top right we have the lowered nozzle type. The bottle is either raised up to the nozzle or the nozzle lowers down into the bottle. Since we don't have a seal around the lip of the bottle, it's just exposed to air, so we're controlling the height from which the liquid falls from the nozzle to the liquid surface as it fills. And as you fill the bottle, the nozzle raises with the level of the surface. So you reduce the amount of air that might get trapped in the flow, so it doesn't have to fall from the very top of the bottle to the bottom of the bottle. Um, this is useful for more viscous liquids usually. On the bottom left, we have the sealed nozzle. The bottle raises up to the white gasket, so it creates an airtight seal so you control all of the gases and all of the liquids that flow in and out of that bottle. Here we'll take a closer look at the sealed nozzle type. In the video it's showing you a closer up of the bottle creating a seal, but you can also see the bit of travel that takes place when the contact is made between the lip of the bottle and the seal. So you can see in step 2 here, after the bottle is pressed up against the seal, it opens up a spring-loaded gate for the liquid to flow. That's that little extra bit of travel in the video you saw. So in step 3, we have liquid flow, and then the air vent that's created also from the spring-loaded release. The air exits through a secondary valve there. Then in step 4, the bottle's full, and the liquid actually overflows into the vent that would usually allow the air to escape. And the liquid flowing into that gate blocks off the airflow, so then you no longer have a pressure difference in the source of the water and the bottle. So in step 5, when the liquid has stopped flowing from inside the bottle, you release the nozzle or you lower the bottle back down, and then you close the physical spring-loaded gate in step 5 there, so you're not still flowing up in the air. Here we're talking about flow regulation. In the top right, we have computer-controlled flow. So you have a digital encoder or a servo of some sorts, and then a pump. And that lets you deliver an exact amount of liquid per cycle. And then that lets you change over bottle shapes, bottle sizes, um, different settings, and because you know the exact amount of volume that you're going to fill per round. On the bottom left, we have the overflow regulated. This is pretty much the system we saw on the last slide, where when the bottle is full, the liquid flows over the air vent hole. And because you want that liquid to stop flowing at a very precise time, you purposely overflow it a tiny bit to fully close off that gate for liquid flow. And that tiny bit of water that seeps into the air vent hole is cycled back to this little tank here, and then that flows back into the product line at some point. Here we have pressurized filling for carbonated beverages. Step 1, the bottle arrives to the nozzle just with regular air inside. Step 2, the bottle creates an airtight seal around the gasket around the nozzle. And a vacuum vent opens up and creates a vacuum to pull all that air out. Step 3, you inject CO2 while also maybe keeping the vacuum open for a little bit to pull all the air out and make sure you have as much CO2 as possible. Step 4, liquid starts flowing. You keep the CO2 vent open so the CO2 has a place to go as you're filling. Step 5 there, the CO2 pressurizes back into the tank at the very top there, and that's what actually allows the liquid to stop flowing. So once the pressure equalizes between the neck of the bottle and the tank at the very top, uh, once that equilibrium comes to rest, then the liquid stops flowing. Step 6 there, the liquid stops flowing and the bottle starts to release. Step 7, you fully pull it away. The mechanical stop on the nozzle is initiated, and the air escapes, or the CO2 escapes there. This slide just shows that as you're filling, you're usually moving or rotating to the next station to where you'll be ready for capping by the time you're fully filled. Headspace is really important for the final product. For carbonated beverages, if the headspace is too large, then CO2 inside the liquid will start to escape to the headspace and create a flat product. If the headspace is too small, then thermal expansion will create pressure spikes, and that just creates issues. For bottled water, it can't be underfilled for appearance, but you have to allow a large enough headspace for the liquid to thermally expand. Also, mechanical shock for transportation is important. The headspace has to be large enough to help out with that. For hot filled products like juices and Gatorades and sports drinks, the pressure balance after cooling is important because it creates a vacuum inside the headspace. So the headspace can't be too large because after cooling, then it will create a large vacuum. So it has to be just right for the stresses inside the bottle headspace there. Also, oxidation is bad for the product taste and shelf life. So the larger headspace will create a larger opportunity for oxygen to be present. After filling takes place, it's kind of a race to the capping station where you want to trap in the gas inside the headspace to create a pressure balance and seal in any gas that you were trying to trap in there. And also,
Capping and conveyance.
Capping process. This stage seals each bottle to protect its contents from contamination, leaking, and tampering. Most high-speed lines use rotary screw-on cappers that can process up to 1,000 bottles per minute. These machines synchronize perfectly with the filler to pick up caps from a hopper or sorter, place them onto the bottleneck, and tighten them using precise torque and downward pressure. The goal is to create a uniform leak-proof seal while keeping the bottle and cap undamaged, ensuring safety and product integrity all the way to the consumer. Each capping system is carefully calibrated for the type of product being bottled. Beverage lines, for example, using torque settings that balance carbonation pressure, while pharmaceutical lines emphasize tamper resistance and sterility. This precision ensures that every container leaves the production line with a consistent and secure seal. At the heart of the capping system is the chuck, the component that directly interacts with the cap. The chuck functions like the hand of the machine. It grips the cap, presses it down with the controlled top load, and applies a specific amount of torque to screw it tightly onto the bottle. Inside the chuck, a magnetic or servo-driven clutch automatically stops rotation once the programmed torque value is reached. This precision prevents under-tightened caps that can leak, as well as over-tightened ones that can strip threads or break tamper bands. Each chuck is custom fit for the bottle style, and quick change designs allow operators to swap heads in minutes when changing product lines. The efficiency of the entire capping process depends on how smoothly bottles move from the filler to the capper. Conveyance systems use belts, star wheels, and timing screws to guide each bottle into perfect position beneath the capping head. Sensors along the line confirm that a bottle and cap are both present before the chuck descends, preventing crashes and downtime. Modern lines also use servo-driven conveyors that automatically adjust speed so that the filler, capper, and downstream labelers all stay synchronized. When properly integrated, the movement appears seamless, a continuous flow that keeps the production line operating at maximum efficiency. The coordination between conveyors and cappers also support worker safety and maintenance efficiency. By keeping the flow continuous and automated, operators can monitor quality rather than manually repositioning bottles, reducing strain and improving workplace ergonomics. Capping and conveyance may seem like simple mechanical steps, but together they determine the overall success of the bottling line. A perfectly filled bottle means little if the cap isn't secure or the line constantly stops for jams. Through advanced torque control, synchronized conveyors, and AI-powered inspections, modern bottling facilities achieve reliable seals, faster output, and greater safety for consumers. Mastering these systems ensures that every bottle leaving the line meets the same high standard of precision and quality from the factory floor to the customer's hands.
Sticker labeling. After bottles are formed and inspected, they move into labeling stage, where precision and speed matter most. First, bottles are aligned and spaced perfectly on a moving conveyor. As each bottle passes, an automated applicator peels a label from its backing and applies it with the exact pressure and placement. High-speed sensors ensure every label is straight, smooth, and bubble-free. If a label is misaligned, the system automatically rejects the bottle or corrects the placement. Finally, labeled bottles go through a quick quality check before heading to filling, packaging, and shipping. The result: clean, consistent branding on every bottle delivered in seconds. Packaging and storage. Once plastic bottles are manufactured, inspected, and labeled, they move into one of the most important stages of production: packaging and storage. This phase ensures that every bottle arrives at its destination clean, protected, and ready for fulfillment. We begin with line accumulation, where bottles exit the labeling system and are directed onto a controlled conveyor. Here they're buffered and organized to maintain an even, continuous flow. Automated guides align bottles in tight, consistent rows, and they approach the packaging zone. Next, bottles enter the case packaging area. Depending on the plant setup, there are two common approaches: manual packaging, where operators place bottles into cartons by hand, and automated case packers, which use robotic arms or mechanical sweepers as shown here. Automated packers group the bottles, lift or push them into corrugated boxes, and adjust spacing to prevent compression damage. Throughout this process, sensors verify that each case receives a correct count. Once boxed or cased, each case moves to the sealing station. High-speed tape machines or hot melt glue systems close the top and bottom flaps securely. Proper sealing is essential to prevent contamination or bottle movement during transit. Every sealed case is then printed or labeled with batch codes, dates, and identification numbers for full traceability throughout the supply chain. From here, the cases travel to palletization. In many modern facilities, robotic palletizers stack cases layer by layer with remarkable precision. Operators can program patterns based on bottle type, case size, and shipping requirements. The goal is always the same: create a stable, uniform pallet that maximizes warehouse space and protects bottles during transport. After after stacking, the pallets undergo stretch wrapping. A rotating wrapper encircles the pallet and layers of plastic film, locking the case into place. This final wrap protects against moisture, dust, and shifting loads. With the pallet fully wrapped, it is ready for storage. In the warehouse, pallets are placed in clean, temperature-controlled areas. Plastic bottles, especially PET, are sensitive to heat and UV exposure, so they must be stored away from direct sunlight and excessive warmth. Proper airflow is also important to prevent any odors or moisture from infecting the bottles before they're used. Finally, when production schedules call for it, forklifts or automated guided vehicles retrieve the pallets and stage them for distribution, whether headed to a filling lane, a contract packaging facility, or a shipping dock. The bottles leave storage clean, organized, and fully protected. From the moment they leave the molding line to the moment they arrive for filling, proper packaging and storage are essential to deliver safe, reliable plastic bottles. It's a process built on precision, cleanliness, and careful control, ensuring that every bottle meets the standards expected by manufacturers, consumers, and brands around the world.